Welcome to the Allen School Symposium. It is a great pleasure to welcome Fan Long. Fan Long is a graduate student at MIT who will soon receive his PhD, and he's very well known for helping us deal with programs that produce errors. Not the ones you've written, but other people produce programs that have errors. He's shown us how to detect them, how to fix them, how to have systems perform correctly despite those errors, and some of his work has really shaken up the entire field. So I'll let him tell you about that now. Thanks, Fan.
Oh, thank you for the really nice introduction. So today I'm going to talk about learning how to patch software errors automatically. I'm Fan Long, and here's the motivation of my talk. So software programs are everywhere nowadays, and those programs now controls our critical bank systems, our power grid systems, our transportation system, and almost every part of our social life. Because of the wide applicability of software, developers have created an enormous amount of programs. So this shows this trend. We have more than 12 million GitHub projects, and it's just one project hosting side. And with this enormous amount of program, we have successfully automated a large part of the daily life. But on the other hand, software development itself is still a manual process. So as the number of software programs continues to grow, maintaining and working on those programs becomes a very challenging task for software developers. So as we all know, software contains errors. So here I will just use a no-point exception, a common Java error as an example here. This is what you will see if you search no-point exception on the GitHub issue database. It will return more than 100,000 different results, and more importantly, maybe it's a little bit small to show on the slides on the left side, there are close to 30,000 of issues that are still open. That means we're running out of development resource to deal with those errors and fix those errors on time. Another thing to note is that if we look at those results, we'll often find similar stories happening in different projects. That developers fail to consider a corner case that involves no value, and then later they write a patch to handle that corner case and fix it. So on one hand, human patches are different because they are handling aspects of different projects, and developers may think they're doing creative things when they write those patches, fixing those errors. But on the other hand, if we look at them collectively, and we will realize that developers are actually doing similar works simultaneously and often fix similar problems again and again in different projects when they are even not aware of. In the end of this talk, we will see that we can even automatically summarize the templates, patterns they use, and use them to fix future errors. So here is the research, the goal of the research I want to talk about today. We want to collectively learn from the past development effort and automatically improve software programs. So here's the high-level idea of the research. I treat the large volume of existing programs not just a challenge that drives and motivates automated techniques, but also opportunity. And this opportunity enables us to learn from past development effort, get useful information. But if we just apply standard learning program on programs and treat programs as a series of tokens or a set of parse trees, what we often find out is that those standard learning algorithms have a hard time to pierce through the complicated program structures. And what we end up learning are often shallow syntactic information. So today, in my talk, I'm going to show how to combine program analysis with learning and inference techniques. So we first use program analysis to extract useful information, semantic information, from individual programs. And then we use learning and inference techniques to summarize the extracted information across different programs and convert them into models and human domain-specific knowledge that can help solve future problems. Together, those techniques enable new kinds of automated systems that can leverage development effort worldwide to assist software developers. So this is a high-level idea of my research, and today specifically, I want to talk about how to apply this high-level idea to automatic patch generation, which is my thesis topic. So now, here's the context. So suppose we start with an application that contains the error. And also, suppose we have a test suite. So you can think it's a set of test cases or pairs of inputs and corresponding outputs. So part of the inputs are positive inputs, which exercise the core functionality of the application, and the application can already process them successfully. The remaining inputs are negative inputs, which correspond to bug report, and they expose the error we want to fix here. So the program currently crashed or produce wrong results on those inputs. So the goal of automatic patch generation is to automatically generate a patch given the application source code and this test suite to fix this error. And of course, after the error gets fixed, the application will be able to pass all test cases. And so this is the problem setting. And the standard way to deal with this problem is called general validated patching. And I'm going to briefly describe this framework. So for this standard framework, we first start with the original program that contains error, and we perform dynamic analysis on the executions to produce a ranked list of suspicious statements, which correspond to potential root cause of error. So here, we use a standard technique called error localization, and those techniques at a high level compares the execution traces of positive inputs and negative inputs, analyze those execution traces to come up with this list. So I will not go to detail for those standard techniques. Once we get this list, then we're going to grab each statement in the list and apply modifications to change the statement and generate candidate patches. So we'll get a lot of candidate patches, and in this validation stage, we're going to use the test cases to validate each candidate patch and try them. And in this process, we're going to collect all patches that are passing all test cases. We call them validated patches. So here is the overview of what I just told you guys. So we start with the original program that contains error. We apply modifications. We get a search space of candidate patches. And then after the validation stage, we get validated patches, which are all passing the test cases. So one thing to note about this framework is that the test suite is the only information we have in the validation stage. So before we work on this problem, and a standard perspective that is adopted by many previous patch generation tools is that because the test suite is the only information we have, so we will declare success whenever we find anything that can pass test cases. So let's see what could go wrong with this standard perspective. As we all know, for large real-world applications, test suite is always going to be incomplete because it is impossible to cover input domain of a large application. So this means that we may have validated but incorrect patches that get around the test suite but still have negative effects or potentially bad behaviors on corner cases. So such negative effects may include, for example, removal of a functionality if the functionality is not protected by test cases, or introduce new vulnerabilities into the program. So this one possibility this framework could go wrong. Another possibility is that if the modifications we apply generate no useful patches, so we operate on search space contains no useful thing, there's no chance we can get a useful result in the end. Or alternatively, another possibility is that if the modifications generate too many candidate patches, then at the validation stage, we will have scalability issues, and we may run out of time budget to find useful results, even if they're inside the search space we have. So of those three cases are actually theoretical possibilities of what could go wrong. Now the key question is whether those cases do occur in practice. So we perform the systematic analysis on the existing patch generation tool, and we analyze publish our results in ICSI 2016 and ISTA 2015, show that those three cases do occur in existing patch generation system results, and they are main challenges for making patch generation systems useful for software developers. So now we understand those challenges, we can think about solutions. So our solution here is we treat test suite as just one source of information. And we're going to learn additional information from human patches, for example, and use this additional information to recognize potentially correct patches. Like we manage to rank them before it goes to the validation stage, and we implemented our idea in Profit. So we use the learning information to determine the patch prioritization order, and then the input to the validation stage becomes a rank list. So we will have a rank list of outputs of validated patches, and hopefully the correct patches gets ranked higher and ranked ahead of those validated but incorrect patches with the learning information. So another key component besides the patch prioritization order is the search space. We want to operate on a search space that covers many useful patches while in the same time remain trackable. So we developed a system called Genesis that can automatically infer from human patches and how human changes code to fix certain types of errors. And then we use the automatically inferred modification rules to generate candidate patches. The goal is to get a better trade-off between coverage and tractability and make the patch generation system more effective. So once we get those two key components right, then here's a proposed usage scenario for the patch generation system. We will investigate the results of validated patch. The developers will investigate results of validated patches, go over the list one by one, and then settle on a patch that eliminates the error without the negative effects. So now, the remaining part of the talk will be focused on how we actually do this, how we learn from past human development efforts, the human patches, to enhance two key components of the patch generation system, how we learn how to rank correct patches, and how we infer the modifications. So the first part of my talk, I'm going to talk about the learning patch prioritization order, how we rank potentially correct patches first. And then in the second part, I'm going to talk about how we infer modification rules. So let's go into the first part, the profit system. So I want to use a concrete example to illustrate the profit system and its idea. So here is a real-world bug in the PHP interpreter. So before 5.3.7, there's a bug in the data period class. And this class has the two constructors, this PHP class. One constructor takes 3 parameters, and another constructor takes one single string parameter. This string parameter should correctly encode all 3 kinds of information, the start date, the interval, and the recurrence of the event, and then it constructs the data period object. So the bug is actually in this alternative constructor, at least at a surface level. So the desired behavior is whenever a PHP program passes an invalid string that does not encode those 3 kinds of information correctly, PHP interpreter should just raise the exception. But what actually happens is that instead of raising exception, it simply crashes when you pass an empty string. So this is clearly a bug, and it's actually one of the major bugs that gets fixed in the 5.3.7, and it goes to the changelog of that version. If we look at the bug tracking system of this particular error, it takes 6 to 7 days for developers to fix this error starting from a bug report with bug triggering input. So we will try to apply automatic patch generation system to fix this error. And here's the root cause of this error. So this shows a simplified code snippet of the constructor implementation for the data period class. Because there are multiple constructors, so this function handles them all, so it tries to first parse parameters and try to parse it twice. Then, after it parses the parameters, there's an if statement that dispatches executions. So the then branch corresponds to the logic handling one parameter case, constructor cases. And the else branch corresponds to handling of constructors with 3 parameter cases. So maybe you have noticed that developer made an incorrect assumption about checking the strlen value is enough to determine which branch directions to go. But actually, if you pass an empty string, the strlen holding the length of the string, of course, is 0. So in this situation, you will get dispatched to the else branch. And actually, this branch is for handling 3 parameter cases. So it goes to a wrong branch and later triggers a segmentation fault. So this is the reason of the error. And we can apply profit on it. And the error localization component of profit correctly localized to this particular if statement. And we're going to apply modifications to generate candidate patches. So profit uses a set of static modification rules to generate candidate patches. Here's one modification rule profit use. So for if statement, it tries to add a new class to loosen the condition. And the hypothesis here is the developer made an error of writing too tight conditions, and this modification rule is designed to fix that particular kind of error. So besides this rule, Prophet also applies all the modifications like tighten the if statement, add a new if statement, copy and replace statement, or add a memory initialization statement. So with those modifications, we can generate a lot of canned patches. And here's one example patch that inside search space. For this particular patch, it redirects the execution to the then branch as long as the str variable is not empty pointer. And this fixes the empty string case. And it is actually semantic equivalent to the later developer patches. So this is the correct patch for this case that we want. Now the key question is whether this is the only patch in the search space that can pass test cases. So unfortunately, we have all the valid patches. Here's an example. So this patch is generated with the same modification rule. It checks the irrelevant global variable, ht. It just happens there's a spurious correlation between ht variable value and the test cases, negative test cases in our test suite, so it can get around all the cases in the test suite. But this still is an incorrect patch because there are all the inputs that can still trigger the crash here. So this is not the right way we want to fix this error. So now the problem is we have two patches, both can pass test cases. How we're going to identify the correct one? So let's see what a human would do. Like, say we put those patches side by side and look at them. If we just look at what the patch changes, it's actually very hard to tell because they're very similar. They all add a check a variable against constant, and that's it. But the human developers will look at the interactions between the patch and the surrounding code. For example, for the left patch, this patch checks the local variable, and it also passes a call parameter in the current statement in the surrounding code, and it is maybe written by previous call before. For the right patch, the developer will find out it checks a variable that never appears in this function and actually used in this whole file. It just happens that it magically makes this program to pass. So without the detailed knowledge of the implementation of PHP, just by looking at those interactions, a human developer would conclude the left patch is much more likely to be correct because it actually makes much more sense here. So this will be the insight that Prophet operates on to identify correct patches. That is, the correct patches share universal features which captures the interactions between the patch and the surrounding code. And we're going to identify those useful interactions and use them to identify correct patches. The hypothesis here is because those features are universal, we can learn from one set of application and use the learned knowledge applied to fix errors in another application. We will validate this hypothesis with our experiments. So with this key insight, we build an algorithm that combines program analysis and machine learning. We first perform program analysis to extract atomic characteristics of each program value variable. So essentially, it's a role it plays on the statement and the operator it participates. And then we define features to track the co-occurrence of such atomic characteristics in the patch and in the surrounding code. Each of such co-occurrence will correspond to potentially useful interactions that we may help to identify correct patches. And then we'll collect a corpus and try to apply learner probabilistic model to prioritize correct patches. So here's a concrete example. So back to this example here, the variable str is checked by a condition in the patch. And the same variable is also a call parameter in the current statement in the original code. So through this variable, it establishes interactions between the patch and the surrounding code, and it will be collected as such a co-occurrence pair. And in this extraction process, we also abstract away the variable names that actually triggers this relationship. This is because different programs will use different variables. We want the extracted features to generalize across different projects. So the actual meaning of this pair is that some variable is checked by a condition in the patch, and also the same variable is a call parameter in the current statement in the original code. Do you have a question?
Can you comment on where you're coming up with these rules? Like, are they grounded in your insight into what programmers do, or some more quantitative basis for that programmers, when they fix bugs in the following way?
So there are two parts of this process. So one part is what kind of atomic characteristics we extract, like what kind of, for each program value. For that part, we simply collect all the information we can get through a traversal of AST trees. So we collect, for example, what operators participate, what kind of statements participate. So there's no like a secret recipe in that part. And the true secret recipe here is actually, instead of looking individual informations, we're looking at the interactions between patch and the surrounding code. And this is the key insight of this work that say, well, whether patch is correct or not depends not just on itself and how it looks. It also depends on how this patch interacts with the surrounding code.
Yeah, the question, I guess, is where's the basis for your believing that's true?
So the basis is when human look at when human look at the patches, they will analyze such things. I would later just validate with the experiment to see if that's actually true. Okay. So besides this pair, we can also extract a relationship like this variable is also address taken before, and it's a local variable and it's a pointer. So for the right-hand side patch, at least we can set checks global variable. So by learning from a large corpus, the machine learning algorithm in Prophet will be able to identify, for example, the first two features correspond to positive features that often occur in correct patches. And the first feature on the right-hand patch corresponds to negative features that really occur in correct patches or often occur in incorrect patches. So we'll prioritize the left patches ahead in this particular case. So let's talk about the general setup for the probabilistic model. So essentially, we want to assign a probability score for each patch in our search space. And we can think of patch as a modification M applied to location L. So we want to assign score probability for pair of ML given program P and a model parameter theta. Here is the formula we use in Prophet about the probabilistic model. So at a high level, it just has two parts. On the right side, it's a standard log lineage distribution based on extracted feature and the model parameter value. And this is a standard way for machine learning algorithm to encode the learned information. And then we also have a prior geometric distribution that encodes error localization information. This part try to assign higher probability scores for those patches modified locations ranked higher by the error localizer. So once we learn this model parameter theta value with this formula, we will be able to compute a probability score for each patch in our search space, and we will be able to rank patches with this formula. So here's how we learn this model, the model parameter theta value. We collected 777 human patches from 8 open source applications, and then you can think those collect patches as a pair of original code and the patch. So we learn a model parameter with a maximum likelihood estimation to get the theta value, and then we will apply the learned to plug into the formula to rank patches. So now let's see what kind of results we can get with this. So we build and configure the Prophet, and it's actually, we build the whole system, including the error localization component and all the patch generation process. And then we run Prophet on a benchmark set that contains 69 real-world defects. And those defects are collected from 8 open source applications. You can see it from the PHP and also Wellshark, include PHP Wellshark, which contains more than 1 million lines of code. And one thing to note is that this data set is actually not collected by us. It's collected by previous people working on patch generation system, and it has been used to evaluate many patch generation systems. So you may notice that there are some interactions of applications between the training set we collect and this one. So to evaluate the ability of Prophet to learn across applications, we actually exclude the revisions from same applications when we do the learning for when we apply it to a particular application's error. So all the results here is the results of when we do the learning across different applications. So we run Prophet on this benchmark set, and in the end, we get validated patches. That means passing test cases for 38 of 69, and the correct patches, that means semantic equivalent to what later developer changes for 18 out of 69. And the patch prioritization order is doing great here. We managed to rank correct patches first for 15 out of 18 cases. So whether this is a great result or not, we can compare with all the systems evaluated on this data set. So here's how Prophet compare with other systems. GenProg and AE are previous people's work using stochastic search, namely genetic algorithm, to find validated patches. And they use the standard perspective that I talked before. So they suffer from both a search-based and a patch prioritization order. And as you can see, although they can generate many patches that are passing test cases, most of them are actually incorrect, and they generate very few correct patches. Nginx is a system that published after Prophet, and it uses a similar search space as Prophet, but it uses SMD solver instead of learning to try to find validated patches that are passing test cases. As you can see on this particular benchmark set, Prophet still generates more correct patches for more cases than Nginx. And to the best of our knowledge, Prophet still holds the state-of-the-art results in this standard benchmark set. So another thing I want to talk about is how important is the patch prioritization order, the learning in the Prophet. So we can evaluate this under our usage scenario. Suppose the developers is going to investigate the rank list of the results. And of course, if we give them too many patches, developers will not look at all of them. So they will only look at the top n patches for each case. Then in this scenario, how many cases they will find correct patches for. This is the evaluation under our usage scenario. And here is a comparison between Prophet and two alternative patch prioritization order. A baseline order that rank patches only based on the locations they modify. And a manual prioritization order we developed before we work on Prophet. And it uses a set of human heuristic rules to rank patches rather than any machine learning. So as you can see, with the learning information, Prophet consistently outperforms two alternative orders, not just a baseline order, but also the manually tuned order. The difference is larger when developers are willing to look at less patches. So what this tells us is that learning information makes patch generation results more useful for software developers. So in the first part, I talk about Prophet system. It's the first patch generation system that learns from past human patches and uses the learning information to identify potentially correct patches, rank them ahead to guide the search process. As our results show, Prophet can automatically fix real-world errors in large applications, and it outperforms existing patch generation systems on a standard benchmark set. One thing to note about Prophet is that it still uses a set of static rules to generate the candidate patches. So when I was working on Prophet, I was wondering, can we actually learn how developers write patches in the first place? And this means that we want to look at a set of human patches and see how human changes the code for fix this type of error, and then infer the code transforms or modification rules they use and use them to drive the patch generation rather than a set of fixed rules. The benefit is first to enable more flexibility to the patch generation system, make it truly automated in some sense. But also in the later, you will see that with the automatically inferred rules for common Java errors, for example, we will be able to get a better trade-off between coverage and tractability and enable the result system to outperform manual rules. So we built a system called Genesis doing exactly this, and I'm going to introduce it in the second part of my talk. So here's an overview of Genesis system. Starting from a set of human patches, the first step to infer the transform rule is actually to do the abstraction and the generalization to summarize the high-level actions developer did in those patches. And here's a concrete example. Suppose we have a patch that fixes no point exception errors. Here, this patch just add a new class to check something against null. After the first step, we are going to abstract away the program-specific aspects of this patch, like the variable names, the expression it touches, just to keep the high-level action what the developer did. Like it disjoins a new class to check against null value to fix an NPE error, so that this action actually can apply to different applications. So once we finish the first step, we'll get a lot of candidate transforms or candidate high-level actions we can apply. Now the second step is we want to navigate the trade-off between coverage and tractability to find out the set of transforms we want to use in the final patch generation system, and we select this set of transforms to generate candidate patches and drive the patch generation. So here's a more intuitive diagram that shows the idea. Suppose there is a space that contains all possible patches in the world. And of course, we will observe many past-human patches. So those are the points that I show here. So the goal here is we want to infer a set of transforms from those past-human patches to cover the dense area of the space. And then the hypothesis is if we focus the search on those areas, the patch generation system will be more useful. So now the key question is how we're going to do this, right? First of all, how we get the high-level actions by observing those concrete patches. So here's how we do it. And the main challenge of doing this is to determine the right abstraction granularity. So we use the previous NPE patch here. So for this particular patch, if we do the abstraction in the most straightforward way, we'll say, OK, get a transform that says it disjoins a new class to check against null to fix this NPE error. If we do the abstraction at a different granularity, for example, more coarser granularity, we can get a more general transform that generate more patches, like just simply replace the condition or add a new class here. And if we do it at a finer level granularity, we will get a more restrictive transforms that applies more focused, more specific scenarios, but generate less candidate patches. We may even consider more complicated cases where we consider multiple choices of operators we choose. So now what's the right way of doing the abstraction and how we determine that? So the solution here we propose is to generalize transforms from not just one patch, but a set of relevant patches. The idea is if a human transform is useful, then it must have been applied to many human patches. And if we look at those patches together, we will automatically find out which part of the change belongs to the high-level action and which part changes belong to the program-specific details. So here's how we do the generalization process. So we look at not just one patch, for example, 3 patches here. And besides the patch I showed before, here's 2 more patches I grabbed in our data set in experiment. They're all fixing no-point exception errors, add a new class here. And then those are from different projects. So I will not have time to describe the detail of the generalization process. At a very high level, this generalization algorithm first converts the original code and the patch code snippet into abstract syntax trees or a parse tree that summarize the code structures. So then we will do the AST matching, systematic AST matching algorithm to find out the common component of those patch code and origin code to find the common elements and structures. Then we convert back to the non-tree form to get the generalized code transform. So this is the code transform we'll get with the 3 patches I showed before. So at a high level, this generalization process keeps the elements structures that are common for all 3 patches. So because there are always 2 nested binary operator expressions here, and there's always a constant no value in those 3 patches. So it will keep and discover this common structure and keep it so it becomes part of high-level action. For the remaining part, it abstracts away the elements that are different. So this enables us to get rid of program-specific details like variables or the original expressions, and then it only keeps the high-level actions. This enables the result transform to apply to not just one program, but multiple programs. So essentially, this result transform says that we're going to conjoin or disjoin additional new clause to check against the no value and to fix NPE errors. And in the generalization process also infers proper constraints for the synthesis of a new code to fill in the hole represented by E, so the bounds about how to enumerate here. So essentially, at a high level, this result transform covers the 3 patches that it derives from, together with many other patches in the training set. And this time, we get very lucky because this transform is very useful for fixing no-point exception errors, at least, because it gives us a nice trade-off between coverage and tractability. It can generate correct patches for many errors, while at the same time remains retractable, the search space size. So this time we get lucky, but are we always going to be lucky here? So what would happen if we do the generalization from those 2 patches? So here's what would happen. We take them and we get their code. We convert them into trees and do the AST matching, find nothing in common, and here's the result transform we would get. So basically, this transform says we replace something with completely new expression statement and enumerate everything inside it. And this is not very useful because it will give us a bad trade-off. Essentially, it will generate too many candidate patches, intractable number of candidate patches for many cases, and harm the patch generation process. So this time, we are not very lucky. So you can think of a sampling algorithm that samples the subsets of training patches and then perform the generalization algorithm on each subset we sampled. Then we will get a lot of candidate transforms, a lot of candidate high-level actions. Now the key question is how we're going to select the set of high-level actions transform we're going to use in the end for patch generation, respecting the trade-off we have. So here's how we're going to do this. So we'll reserve part of the training patches as the validation patches. And then those validation patches can be used to evaluate the transform we get. For example, apply the transform to the original code of validation case and to see whether this transform can actually generate back the reference human patches. This tests the coverage of the transform. And also, we can see how many candidate patches the transform generates in total. This tests the tractability. So we can think about this kind of evaluation between each pair of transform and the validation case, and then we will get the following informations. Like the first transform covers the first 2 cases in the validation in the slide, and the second transform, because it's a subset of the first transform, so it covers only the second case, but the result search space is smaller. The third transform covers the third case, and the fourth transform is similar to the one that I talked about before. It's theoretically can cover all 3 cases, but in practice, it generates a prohibitively large number of candidate patches. So we want to avoid such transforms. So the goal is to select a set of transforms that respect trade-off we have. For example, we can select the first one and the third one, covers all 3 cases in the slides, and produce a reasonable search space size. We want to avoid selecting 2 overlapping transforms or transforms that blows up a search space. So it turns out that we can formulate this problem into integer linear program, which we encode the evaluation results into 2 matrices G and C, and then we define the 2 set of variables where X denotes whether we cover a validation case and Y denotes whether we're going to select transform. Then we can specify our trade-off into ILP formulas. So the objective here is we want to maximize the number of covered cases. So because X denotes whether we cover a case, we sum over all X. Then the first group of constraints at a high level defines the meaning of coverage. It means that at least one of the select transforms should be able to generate the reference human patches for each covered case. Then the second group of constraints at a high level specifies the tractability constraints. It says that the total number of candidate patches for each covered case should be less than a threshold beta, which is determined by our computation budget. So with those formulas, we can ask the off-the-shelf solver to return the optimal set of ILP solver to return optimal set of transforms that respects the trade-off between the coverage and the tractability. And this will be the final set of transforms we're going to use to generate patches and drive the patch generation process. So let's see what kind of results we can get with this inferred transforms. So to evaluate Genesis, we collected from a top GitHub Java project more than 500 null point exception errors, 200 out-of-bounds errors, and 300 class-cast exception errors. We focused on those three kinds of errors because there was a prominent patch generation system for Java called PER, and in PER, the author designed manual transforms for those three kinds of errors. And we want to compare those inferred transforms with those manual transforms in PER. So we further collect test cases in those repositories where we find those errors. And it turns out that for 49 of those cases, we have the test cases that triggers the error. And so we have the original code, the test cases expose the error, and later developer patches. So we can use them as testing benchmarks for testing the patch generation results. For the remaining errors, we'll use them in a training data set to do the inference to produce a transform. So here's the result setup. Here's the experiment setup of Genesis. We apply Genesis to infer search spaces for three kinds of errors with the training patches we collected. And then we run Genesis patch generation process with the inferred search space to generate patches for the 49 benchmark errors. And we compare the results with the results of manual transforms in PER. So here is the results of Genesis for NPE errors. For the 20 NPE errors we collected, we managed to generate correct patches for 13 out of 20. That means semantic equivalent to the later developer patches. And we have a similar result for out-of-bounds errors. We generate correct patches for 6 out of 13. And we generate correct patches for 5 out of 16 for class-cast exception errors. We can compare our results with the manual transforms in PER. So here is the results we get. Note that in our experiments, to ensure the fairness of comparison, with our best effort, we re-implemented the PER manual transforms within our framework. So everything else of the patch generation process is the same, except the search spaces they use. So as you can see, Genesis can consistently generate more correct patches for three kinds of error. And the reason is because we operate on a more diverse set of transforms.
Are these correct patches ones that pass all the test cases, or are they the same as what the developer did?
Yeah, those patches are semantic equivalent to later developed patches. So if you count the validated patches, it will be much more. I would love to share the detailed number too if you're interested. So here is a slide that summarizes a high-level template that Genesis inferred transforms covers for null-point exception errors. So without any heuristic knowledge about what NPE errors are, just by looking at the developer patches in the past, Genesis managed to find out that it is useful to conjoin the disjoins class, add if guarded exception flow or control flow statement, got a conditional expression, got an existing statement, or switch invocation order to fix NPE errors. Well, in comparison, PER transforms only do add if guarded return statement or guard a single existing statement. What this tells us is actually manually design those transforms are hard, not as easy as it seems, because there are so many design choices you can make. For example, you say, I want to add a transform that says add if guarded return statement. Then you want to determine what kind of values you're going to return, and how you're going to determine which expression you try to check against null, and whether you want to consider all the control flow statement. All of those design choices will have their own implications on the trade-off between coverage and tractability. It is very hard for human developers to navigate this trade-off space. So the philosophy of PER mentioned in their paper is that to include only the most common patterns to avoid search space explosion. And therefore, it misses many useful templates. We have similar stories for out-of-bounds errors where we have a diverse set of transforms, while PER only add the if guarded return or got a single statement to actually check index out of range. Well, similarly, for the class-cast exception errors, where we have a diverse set of transforms, this is not even the complete list of it. Well, the PRR only add instance of or change cast type, and that's it. So this explains the reason of the different results we get. So here is a summary table that summarizes my work of Prophet and Genesis in the context of related work. Automatic patch generation has been an active research topic in software engineering and the programming language community. And the main difference between our work and other works focusing on fixing large programs is that we treat test cases as just one source of information, and we're going to learn additional information from past human patches and use them to guide the patch generation process. Prophet and Genesis are the first systems operating with this new perspective, and we are happy now more people are following this direction to build patch generation tools. So now I have to talk about the two patch generation systems I built. I want to view them at a more higher level. The common things of those two systems is that they both learn from past human development effort, and namely human patches, and use them to guide the patch generation process. So the experimental results here actually demonstrate the power of an idea of combining program analysis with the learning and inference techniques. And the automatic patch generation, I believe, is just one example of applying this idea to automate the software development process. I believe there is much more we can do besides patch generation. In fact, the big picture of my research is always about develop automated techniques to make software programs better. So besides patch generation, in the past I've been working on input filtering and rectification techniques, which detects potentially malicious inputs that can trigger vulnerabilities in your program, and then discard or change those inputs to stop the exploitation. So I developed first sound techniques to generate input filters for critical integer overflow errors. So I also work on the first code transfer techniques, for example, that can transfer useful code such as security checks from donor application to recipient application. I work on the first program synthesis tools that can synthesize parser programs from natural language descriptions about the input format. I developed the program recovery techniques that can enable the off-the-shelf binary program to recover from fatal runtime errors with negligible overhead. And I'm generally interested in automatic bug finding, analysis of security attacks, and the recall and replay techniques. So looking into the future, I believe as the number of software programs and our dependence on those programs continue to grow, automated techniques will be more and more important. My research on Prophet and Genesis, or the code transfer techniques, which I did not have a chance to talk in detail today, I believe demonstrates that the growing volume of the existing program is not just a challenge, but also a great opportunity. With this opportunity, we can think hard about what we can learn from past development effort, like what's the correct way to write code, and what kind of patterns developers often use to change code, not just for bug fixing, but maybe for code refactor, etc., and what kind of different implementations we have for similar functionality and protocols, and exploit this opportunity. So to fully exploit this opportunity, I think we need new kinds of analysis and inference algorithms that can deal with a large amount of programs and also meta-program informations like inputs and Stack Overflow pages. And this requires us to combine program analysis techniques that are based on formal reasoning of one program and a machine learning technique which is about statistical inference of a large data set. So to bridge this gap, I believe we need to keep working on new abstraction frameworks that can capture common semantic properties of programs and convert them into models amenable for machine learning algorithms. And we also want to develop new machine learning models that can capture that full program and capture not just syntactic level information, but a deep semantic level information about programs like a data flow path or control flow path in the program. If this research direction becomes successful, I believe it will completely change the software development process and the software industry. We will have a chance to use bug fixes or vulnerability reports of one program to enhance another program. And Also, developers will have a chance to focus only on the creative part of software development. If some functionality exists somewhere else, then they can use new program synthesis or code transfer techniques to brought that implementation details here and don't need to reinvent the wheel. I believe this will be a much brighter future for software developers. I want to keep working on this direction to make all of this happen. So I'm happy to take questions. Good. Mm-hmm.
So when a human fixes a bug, the first thing that they typically look at is exactly what type of failure it is, the details of the failure, which gives a lot of information and would greatly shrink the search space. As far as I can tell from what you're saying, you're completely ignoring this information. So could you say a little bit about why, and would it be something you want to incorporate in the future?
It's not saying that. I mean, we're not like completely ignoring that part. So that part we are using standard like error localization techniques to perform dynamic analysis to identify potential locations to change. That's part of the system. It's just that's not focus of the system. But I think it's true that patch generation systems and human developers are definitely going to operate in different ways, right? Because they have a different strengths where human developers, if they're willing to spend their time, they can follow, and if they're smart enough, they can follow the longest logic chain in the program and reason about it. While the power of a patch generation system, or this, is it has computation power, and it can try multiple things, and it's impossible, so it can search through many candidate solutions rather than just has to be settled on one and then try that.
So you're saying you actually do use the actual details of the error to...
Yeah, so the error localization techniques, for example, will take into account how the statement gets executed by different inputs, by failing input and the failing input and the passing input, and compare the traces to come up with details. There are techniques, standard techniques will look at the statement coverage, and also there are more advanced techniques about look at the dynamic invariance that gets violated into negative trace and see whether they can infer and get a more accurate result of error localization. But yeah. Mm-hmm.
Will your robots take developer jobs away?
Could you say your question again?
So the future that you painted looks interesting and benign, but maybe your robots will eventually eliminate developer jobs.
Well, I think my position, personally, I don't believe that will happen in relatively soon. For example, the techniques, I think I would say that the goal right now is still to develop there's a lot of repetitions in the software development. I want to create automated tools to help developers to make the development process more enjoyable and also less repetition, and just kick out the boring part of it. I don't believe I will kick out the software developers as a whole. I mean, even if that's possible, that's probably a very long-term goal, not in any time foreseeable.
Can you speculate which task will be eliminated last?
Which task will be eliminated last? I think the task will be eliminated last is about making decisions about what to implement, right? Whether I want a feature A or feature B, I can't see a way that we can automate that soon. Yeah. And also, another part, I think there's another part that if there's anything that are tied to not just the exact right or wrong, for example, for UI designs where you want a beautiful UI to attract people, then I cannot see how to completely kick a human out of the loop. Yeah.
A little more specifically, and maybe even seriously. We've automatically generated code for decades with compilers, and this clearly takes it in a new space and leverages the opportunity of big code and all that. But sort of code design and readability is something that when you have a million-line program and you're trying to patch even a few dozen bugs, I'm all for the computer doing it. The computer knows why it's doing it and doesn't make stupid mistakes. But as you're moving towards these future directions, if you rely on the, do you worry about the humans and the automated procedures working together, given that they have very different notions of readability and understandability?
Yeah, I think this is a very legitimate concern. And so right now, there was work that I know one work was talking about patch maintainability of the patch generated. But so far, the main focus is about generating right patches first. So now but because that's something that comes before the maintainability, if you generate something that is bad or have a negative effects, then maintainability does not, because you don't want to maintain that code, right? I treat that as I would say more harder problems than maintainability or code styles. You can think about, if we apply the same idea about learning from past code, I would see if we know that what we're doing is right, just about change the way we write it to fit in the code style, there will be much more tools and the things we can learn from the past humans, like the way they do the indentation, the way they name the variables, etc. Right? And I think that's actually what the learning, combined learning, and the program analysis can help too, and probably doing better than that. Mm-hmm.
So some previous work has on real bugs has found that 76% of all bugs have fixes that are longer than one line. I think it's quite remarkable that your system has automatically learned these patches, and they're all pretty simple. Mm-hmm. And you got really good results. So is this because you were focusing on particular types of bugs, just null pointer exceptions and out of bounds? Mm-hmm. And can you speculate on the possibilities for this sort of learning to either find much, much more complicated bug fixes, like the ones that dominate, or what the possibilities for generalization are?
Yeah, I think this is a very nice question. And I actually, so I think I'm not supposed to, I don't believe these techniques will going to fix all errors. And there are certainly kind of errors outside scope. For particularly this, because it's a search-based technique, so it's tied to the amount of modification that are required, right? So based on our experiments, working on a lot of errors and do the collection, and also it's roughly aligned with what you're saying, or the work saying that a little bit over 50% of those errors we believe are outside scope. So here's an example. Basically, it needs to rewrite a whole function or have a lot of changes. And I believe it is outside of the scope of current techniques, and I don't see any search-based techniques can get out of that, just because the search-based explosion when you want to search through all this kind of changes. And well, if you think about profit, that's kind of the right situation where we have a fixed errors for 18 out of 69, so it's roughly like 20 to 25%. There are another like 20% errors, slightly more than 20% errors. It's like we kind of get it, but still fell short because some complicated expression to synthesize. For example, this one is actually a real class-cast exception error we're collecting our benchmark set. So it's at the instance of check. That's one we get, but it actually returns a very complicated constructor call, and that's very hard to synthesize and enumerate directly. Well, maybe in future, we can explore, for example, parallel structures around to synthesize a particular case. So there's some improvement that we can do in that respect. And I think, yeah, you're right for particular case of errors, like null point exception errors, out of bounds errors, where the fixes tend to be small. So we are getting better results on that compared to profit, where it's a set of a general class of error we collected or past people collected, and we get roughly 20%. And that's to see. I think there are more room of improvement in the future. And well, just one thing to note is that the Genesis, although we evaluated on the three kinds of error, but the techniques, the inference technique itself is not limited to that three kinds of error. We're actually not taking into any heuristics about a specific error. As long as we can collect enough training patches for one class of error, we can quickly adapt it to another class.
Other questions? Well, let's thank our speaker.
Thank you.